In the meantime, 5.1 exponent property. So, we saw a little bit of exponents when we evaluated expressions, but now we're going to look at exponent properties, particularly when they're associated with variable type bases. So exponents, I don't know, to me it's kind of a nerdy way to explain that you got two parts to this exponent stuff, okay? You got the x here, and of course that x could be a number, could be a letter, it doesn't really matter, but that's what we call the base value, and that's the value that's going to be repeatedly multiplied. Well, maybe I shouldn't do it right there. The base, yeah, I'll put it in there. Value repeatedly multiplied. Ooh. There we go. All right, yeah, the base is the value that's being repeatedly multiplied. But then you've got the exponent up here. And yeah, it is called exponent. So I'm just going to write that in. There's the exponent. Which tells you how many times to multiply the base. Maybe make that fit. There we go. Okay. So that is the exponent. Everything else we see is a pretty nerdy way to understand exponents, which, if you want to, that's fine. As long as we understand it's repeated multiplication, that's kind of the important part. The rest of us will be helped by seeing what happens with patterns and stuff like that from the exponent. So like this one, we don't want to evaluate this to be a gigantic number. We just want to write this in exponential form. So remember, for this then you're going to have a base. We'll put that in this box. That's where the base will go. And then the exponent is kind of a smaller number in the upper right-hand corner right here. That's our exponent, right? So the base, yeah, that's the number that's being repeatedly multiplied here. And from what I can tell, that's our 8 on this one. Okay, so we just put an 8 right there. I don't care how many there are. It's just that is the number that's being repeatedly multiplied. And then the exponent is how many there are. Well, we can go and count them up here and see if I can make this work. There's 1, 2, 3, 4, 5, 6, 7 of these 8s. So that means our exponent is 7. So this is, and it even reads, this would be 8 to the power of 7, okay? Now the nice thing is with mathematical symbols, it does shorten that so we don't have to write all that garbage. Well, I think it's okay, well, whatever. So another word for exponents, yeah, you'll hear it referred to as powers of values, but again, it's all in relationship to the base. All right, as long as we can write these and understand what it means to have a base and an exponent right here, because I'm going to be using this vocabulary quite a bit. Bases and exponents, okay? We're going to be using this vocabulary quite a bit, of course, in this module, but probably in the next module too. So negatives and exponents. Your answer positive or negative? How many negatives are there? A negative and negative. Yeah, okay, so just some rules for determining if your answer is a negative or positive. Just remember in your order of operations, exponents come right after parentheses. Now, we just learned that exponents are also repeated multiplication. So they just kind of actually fall under the multiplication category, but we have to expand that first before we start to operate, which is why exponents come first. So, yeah, you're going to be asked to evaluate some of these, like these, okay? So, yeah, well, let's go ahead and evaluate these. But before I do that, and yes, the calculator will do that. I'll show that in a second. But let's do these without the calculator first, just so you understand what's going on. All right, I'm going to start with this -5 base to the power of 3. That means that I need this -5, and I'm going to keep it in parentheses, by the way. I need this -5 3 times. There's 2. There's some technology here. There's 3 of them. And yes, it's all repeated multiplication, which you could put in there if you'd like. okay? Now, what we're seeing on that last slide was, is the answer positive or negative? Well, since we are evaluating these, for this first problem here, I see that there's 1, 2, 3 negatives. 3 is odd, which would then make my answer negative. After that, all you got to do is, 5 times 5 times 5, which is 125, okay? So our final answer here ends up being negative 125. Now, would the calculator have done that for us? Yes, but that's not the point here, because most of the problems we're going to see today, you won't actually be able to use a calculator to evaluate them, but it will be important for you to understand what is happening when we do see those numbers, because you will have to evaluate the numeric parts. Now, we've seen a problem like this before with the exponents when we went over order of operations stuff, okay? You'll see on this one that it is an order of operations type problem, because this is not a negative 2 to the power 4, meaning you don't have 4 of these. You don't have this one, and it's not like you got another one and then another 2 of these. You see what I'm saying? And then you say, well, these are all multiplied. That's not what this is, okay? All right, here's what this is. What we have here is 2 first to the power 4 because of the order of operations, which means that I would have 2 in parentheses like this, but I would need 4 of them, right? So there's a second one. And yes, these are all being multiplied. There's 4 of those. Okay, well, what about this negative out in front? Well, it's kind of like saying that you got a negative 1 out there in the front. It's being multiplied by all this stuff as well, okay? So it is a multiplication problem, and we can solve that. But is the answer positive or negative first? Well, I see only one negative. 1 is odd, so the answer is a negative. 2 times 2 is 4, times 2 is 8, times 2 is 16. So we should end up with a negative 16 answer on this one, okay? But it's not negative because of the 2. It's negative because of the negative on the outside right there, okay? And if that 2 were negative, and there was no negative on the outside right there, let me just, I should show this. Negative 2 to the power 4 like this, that would end up being a positive 16, because from the expanded multiplication right here, you'd end up with 4 negatives. 4 is even, which makes the answer a negative right there, okay? Well, that was real fun, but like I said, the calculators will do this for us. Well, how do we get the calculator to do it for us? Just type it in. That's all you got to do. So this negative 5 to the power of 3, first I'd open up a set of parentheses like this. Then I'd push the negative button, not the minus, and then 5, and then I'd close that set of parentheses. Now, to access the exponent of 3, you got to push this button. It's for the calculator that I've recommended in this class. It's 1 button to the left of 7, and then one button up. It just looks like an arrow. Mathematically, we call that a caret because we're nerds. Okay, then you push the 3, push equals, and it'll give you that negative 125. Okay. And so that second problem, right, you type the negative in first. Again, it's not the minus sign. And then you'd open up a set of parentheses, then a 2, close your parentheses. Now you need that exponent button. And you'll see, even when you push this exponent button, the calculator will go into what I call exponent mode. And so it's a smaller box to the top right of your parentheses 2. And once you type in 4 and equals, then it'll give you that negative 16 right there. So my recommendation is when we get to the numeric part, yeah, we'll be using a calculator like we did on these two. But we have to be able to do this with the variables as well. All right, so we can do the same thing here with 1/4 to the power of 3, right? It did say to, evaluate, okay? So I'm just gonna expand this. I'm gonna show it as 1/4 here in parentheses. By the way, the calculator will do this, but I just want to demonstrate what this is with the exponents, right? So I got 3 1/4 all being multiplied together. And I'm just going to do fraction multiplication because the numerator is pretty easy. 1 times 1 is 1 times 1 is 1. I get a 1. And then in the denominator, 4 times 4 is 16 times 4 is 64. 1/64. Okay? Now, we may revisit this problem here in a second, but for now, it's just important that you can see that you can evaluate, even if they're fractions. Could you have typed this into the calculator? Yep. Parentheses n over d, though. You're going to use the n over d button, the fraction button on our calculators. Close that parentheses, put the exponent of 3. It will simplify that into 1/64 for you. All right, so this brings us to our first rule. It's usually called the product rule, not that I think anyone really cares. The main thing you need to notice about this is that the bases are the same. We have the same bases on this one, right? They're both x's. What this will produce for us is a same base answer. And of course, maybe it's not x, maybe it's a number, maybe it's a different letter, it doesn't matter. But what you do with the exponents a and b here is you're going to combine them with addition. Okay, this will be a way to simplify problems that show like this with a very quick rule. Let's see if we can find a good example to demonstrate this, though. Yeah, this is a good one. This is pretty good. So we got z to the power 4 times z to the power 3. Now, just by the rule that we saw, the base will not change. It's still going to be a z base. Then what do we do with these two exponents, 4 and 3? Well, we're just going to take them, and we're going to add them together. Okay, this would result in z now to the power of 4 plus 3, which is now 7. Z to the power of 7. Now, I'm going to show this once just so you can see what is happening, why we are able to just add the exponents. Because a lot of students get confused and say, why are we able to multiply? Why is it multiplication here but addition here? Here's why, okay? So I'm going to take this z to the power 4, and I'm going to show it expanded. 1, 2, 3, 4. 4 z's, right? And then I'm going to take z to the power of 3, and I'm going to expand that as well. 1, 2, 3. Now remember, this is being multiplied right here. So I'm going to multiply all of these z's together. Well, notice they do have the same base as we saw. So the base will not change. But how many z's do we have now? 1, 2, 3, 4, 5, 6, 7. So you get z to the power of 7. Okay? Now this is a nice shortcut, I think. Are you able to just expand and simplify? Sure, if that's what you want to do. Okay? But you'll see you'll end up with the same answer. But this is why we're able to add the exponents, because remember, there were 4 z's and 3 z's, and so when we're multiplying the same bases like this, we get to add those exponents like that. I hope that wasn't too freaky right there. Okay, so let's use the rule on this, okay? So let's simplify this just to save us some time. We can see that the bases are all b's. Now, if there were different bases, of course, we would not combine those exponents. These ones are all the same base. They're all b bases. So we get to look at the exponents. Now you'll see the 2 and the 9 exponents. Okay, there's an exponent for this b right here. You just can't see it. And since we can't see it, it's a phantom value. In this case, specifically, it is a phantom 1. So really, we have exponents of 1, 2, and 9. Since the bases are all being multiplied, we are going to be adding the exponents. So just a little bit more space here. But the base, of course, will not change. But 1 plus 2 plus 9 is going to give us a new exponent of 12. And this b to the power of 12 is our fully simplified expression now. The main objective for this problem is that you understand if you do not see an exponent for any value, this could be a number, by the way. If you don't see an exponent for it, the exponent is automatically a phantom 1, okay? Because we're going to need that when we get into some of the other rules. All right, well, this just turns the fun knob right up to 11, right? So there's more bases on this one. There's numeric bases as well. So we're just looking at the same bases, though. That's the only way we can use the rule, this product rule that we've just learned about. Now, you'll see numerically, though, you've got a 3 and a 4. By the way, this is all multiplication. There's multiplication between these two. In fact, there's multiplication here, 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 and here. So those parentheses aren't really doing anything for us, except to say that we've got two different expressions. Somehow they're separated, but we could combine them if you would like, meaning that you could erase those parentheses, if it helps. I'm not going to because it's all multiplication. It's just extra work. So I'm going to start just by combining my 3 and 4 right there. Now, when I say combine here, this is multiplication, right? So I'm doing 3 times 4, which is 12. So there's that base. Now, is it possible that sometimes you'll have other exponents with the numeric bases? Sure, but right now there just isn't, so I'm not worried about that. Now I'm going to look at my x bases. Okay, so I got this x base and this x base. It's all multiplication. So you could, if you wanted to, technically bring these together, x to the power of 3 times x to the power of 4. Yes, this is a little work. That's okay if you want to do it. But since they are the same bases, by the way, by bringing them together there, that's just the commutative property of multiplication. You're free to do that. Not that I think anyone remembers that it's the commutative property, but it is. We're just going to add those two exponents, which leaves me with the exponent 3 plus 4, which is 7. So I end up with x to the power of 7 when I combine all of those x's. Next up, let's look at our base y's right here. We got some base y's. So let's look at this over here. So I got y to the power of 5. And I also got y to the power of 2. So that would be y to the power of 5 and 2, but we'd add those exponents because the bases are being multiplied. 5 plus 2 gives me another exponent of 7. It's just now for the y's, okay? Now we do have the z base right here, but there's no other z's to combine it with, so it's just z to the power of 6. It just remains. And this would be considered the fully simplified expression of multiplying these two expressions originally. Like I said, you're completely welcome to expand these to make 7x's and then 7y's. Again, if you can understand this addition of the exponents, then you give yourself a little bit of a shortcut. All right, how about the power of a power? Well, if you have some base, and again, this a right here could be a number, could be a letter, doesn't matter. It could be an x, it could be a y, doesn't matter. What this means to us is that you're going to take that same base, the base will not change here, but the two exponents, m and p, I'll try to color code these. The m and p, something will happen to them. If the base with the exponent is in parentheses, we're going to multiply those two bases, okay? So this is our second operation with exponents. The first operation was the product rule where we add the exponents, but now we see if you have a set of parentheses, it is possible to multiply the exponents, which we will explain with a decent example. Hopefully we can find one. Like this one. Yeah, this one's okay. All right, let's make this bigger though. So we're going to simplify this, right? Here's what I got. I got this in parentheses to the power of 3. Now, just for a second, what I'd like you to do is pretty much ignore, there we go. Ignore what's on the inside of that parentheses. Doesn't matter what's on the inside right now. Just by the order of operations, I'd have to work with that power of 3, okay? So what I'm saying here is that we're going to take this, whatever was on the inside, and we're going to need 3 of them. 1, 2, 3 of them, like this. Now, of course, there's a rule. Take a little bit of a shortcut here, right? Now that I've got those 3, now we can think, well, what was on the inside there? You got a negative 2 y to the power of 12. So we're going to need 3 of these. And that's really fun to write out. And yes, it is true that these are all being multiplied. And that's multiplication right there, okay? And just like we did on the last problem we did, not the rule, but 2 slides ago, is you can start combining essentially like terms, right? And this is all just multiplication. So I'm going to take my negative 2's here, and I'm going to multiply those out. Negative 2 times negative 2 times negative 2. Well, there's 3 negatives here, which makes the answer a negative because of the odd number of negatives. 2 times 2 is 4, times 2 is 8. So I end up with negative 8. That will be my leading, I guess we can call that the leading coefficient. Then you got some y's right here, y's to the power of 12. So I got y to the power of 12, y to the power of 12, and y to the power of 12. These are all being multiplied. They're the same base. So I'm going to keep that base, but I'm going to take my 12 exponents, 1, 2, 3 of them, and I'm just going to add those together. Okay? Of course, we know that 12 plus 12 plus 12, you can put in the calculator if you need to. That's not something you should feel ashamed about, but that's going to be 36. So simplified, I get negative 8 times y to the power of 36. Now, if that helps you to expand like that, then do it. But can the rule help us? Yep, of course it can. In fact, let's demonstrate that. I'll do it again below here. So let's start with what we had in the beginning. Negative 2 times y to the power of 12, all to the power of 3. Now, before we do this, it's important to understand that this 12 exponent only applies to the y, not the negative 2. Remember, if you can't see the exponent for a base, it automatically takes an exponent of 1. So I'm going to show that phantom 1 right there, exponent, okay? Well, from the rule that we just learned, this means that you're going to take those two bases, -2 and y, well, I'm going to show it as y to the power of 12, and even -2 to the power of 1. All I would do here, and I will want that -2 in parentheses, by the way, because it as a base was in parentheses here. All I'm going to do is multiply those exponents by 3. Okay, so you see how we get y to the power of 36 there from 12 times 3? And then, of course, we've already evaluated -2 to the power of 3 right there. Okay, so that's where this -8 business comes from. Same answer, different strategy. A little bit of a shortcut there, although sometimes it does seem like it's a little bit, it can cause a little bit of confusion because exponents are pretty new to us. So yeah, I get it. All right, so think about what we just barely did and the rule that we applied. You're welcome to expand if you'd like, or use the rule on this one, but try this one out. Take a minute, try it out, and then we'll go over it. Now, kind of a, I don't know, maybe you can call this a shortcut. And I'm going to show this a little different, okay? But we are going to simplify this. Now, for this little bit of a shortcut and this little bit different of a strategy, it's the same strategy, just shown in a different way. It's important to acknowledge all of the exponents on the inside of the parentheses, like this 5 to the power of 1. Okay, there's that phantom 1 right there. Some students even prefer to think of this as distribution with just the exponents. So that means you're going to keep your bases, 5, x, y, and z. But what I'm going to do is I'm going to take this 5 exponent and multiply it by all of the exponents on the inside. So that ends up being 5 to the power of 1, but now times 5. And then it'll be x to the power of 7, but now times 5. So yeah, I think I'm showing more steps than most students usually ever show, but I hope it kind of hits home with what's going on here. You got z to the power of 3 times 5 as well. Okay, well, what will this give us? Well, it'd give me 5 the same bases on this. But now the 5 has an exponent of 5. X has an exponent. 7 times 5 is 35. Kind of big right there. That's okay. Y to the power of 4 times 5, which is 20. And z to the power of 3 times 5, which is 15. Now, as nice as that is, remember that if you have bases that are numbers, make sure you evaluate those. I just put it in the calculator because I didn't actually want to do 5 times 5 times 5 times 5 times 5. I think I hit all of them. So I just put that in the calculator. 5 to the power of 5 is 3,125. The rest of that, yeah, it was the same. I feel pretty good about that. So again, if you most students don't usually show this step, but they usually will show this one right here with the distributed rainbows. Hey, whatever works for you, okay? We'll see that. That's this one, okay? X to the power of 5 over y to the power of 8. Once again, it's the same idea as we saw in that last one. Let's make this a little bigger, though. I'm just looking to distribute this 5 into both exponents. It's not going to change the location of either one of the bases here. So we had x to the power of 5 and x to the power of 8. But now we're going to multiply it by the 5 from the outside of the parentheses there. And that will give us new exponents for both x and y. So 5 times 5 there is going to be 25. In the denominator, 8 times 5, boom, 40. Okay, now if these bases were the same, by the way, that would give us a new rule, which we will see, but just not quite yet, okay? Of course, you're welcome to expand this 5 times if you'd like and then add the exponents. You'll get the same answer, though. All right, how about this one? We're going to do the same thing on this one that we just did on that last one. But again, it's on the inside of the parentheses, that 5. It's not showing the exponent. I would like to see that exponent so that I know what I'm multiplying that 3 by. And I'm really only suggesting this while it's kind of new to us. Once you get a lot of experience, you'd be like, I don't really need to see that exponent of 1, which is fine. But for now, I really do hope it helps, okay? So I'm going to take the values from the inside of the parentheses. Not really doing it. I'm just working with the exponents, I guess. So there's 3. I'm going to distribute to the 2, so 2 times 3, and also the 1. So 1 times 3. This give me new values of exponents. It's not going to change the bases yet, but z to the power of 2 times 3 is 6. 5 to the power 1 times 3 is 3. And yeah, we can evaluate 5 to the power 3 on the calculator as it will want you to on the homework. So that's z to the power 6 all over 5 to the power 3, 125. There we go. That's simplified. So this is this quotient of powers rule here. Again, just like it was with the product rule, or product of powers, I guess. It's important to notice that the bases are the same. When the bases are the same, what you can do is you can take the same base, and you're going to take the two exponents, m in the numerator, and then p from the denominator. And with division of the same bases, you will be subtracting the exponents. Okay? And again, there's a reason why that is, which hopefully I'll be able to demonstrate in the next problem. But this is the rule. If you have the same bases, you can take the exponents from those bases if they're being divided, and then subtract the exponents instead. But again, the base will remain the same. Here's why. So I'm going to apply the rule to this one first, and then hopefully that kind of demonstrates how the rule works. So z to the power of 12 over z to the power of 5. This one, it's the same base. It's a base z on this. But I'm going to take the exponent from the numerator, 12, and the exponent from the denominator, 5, and I'm going to subtract these. And it does have to be in this order, by the way. So now it's z to the power of 12 minus 5. I get 7 out of that. Z to the power of 7 there. All right, now that's the rule, and it's strictly the rule. But can we show this with, or why the rule works? Sure we can. Okay, so, but I'm going to need a big old fraction right here. So I got this z, 2, 3, and here's 4 z's. These are all being multiplied, by the way, or we can pretend that they are. There's 8 of them, and then 12. Maybe I should have made that line longer. That works. Then I need 5 of these. I need 5 z's in the denominator, like this. Okay, in fact, I don't know. You can put them, you can put them wherever you want, just as long as they're in the denominator. Okay. Well, what you should notice at this point is that, at least going back to fraction, I don't know. I guess it would be prime factorization for simplifying fractions. That's all we're looking at this point. Is any value divided by itself is 1. Now in the past, I think I've said this before, but if you see values crossed out like that, it doesn't mean that they just go away. When I cross these out, that means that I'm making a phantom 1. That's a 1 right there. Could you do it diagonally like this? Sure you could. I don't care. It just, anything in the numerator will cancel the same thing, well, they say cancel, but it will make a phantom 1 with anything that's the same in the denominator. So I'm just going to, there we go. There's a bunch of phantom 1s, okay? Well, what just happened right there? See how we took some of the z's from the numerator and we pretty much subtracted the z's from the denominator? That's why we're using subtraction here. Okay, well then what are we left with? See if I can fit this in here. The base is z, that's fine. And these are all in the numerator, but how many are there? 1, 2, 3, 4, 5, 6, 7. 7 of those z's, so that's z to the power of 7, just like we saw when we used the rule. Now, if you need to continue using this expanded stuff in order to understand what's going on, feel free to do that. But once you understand that you can use this rule, again, it's kind of a quick shortcut right there. All right, so here's a big problem, right? Lots of different bases, that's fine. Like I said, I kind of like to start with the numeric values. So I'm going to start with just the 40 and 34. And it's a fractional value, so I'm pretty much separating it from the x bases and y bases, just the same that I'm going to be doing with the x and y bases, okay? So 40 34ths, can this be simplified? Yeah, it looks like it can. It's at least divisible by 2. Well, I guess the calculator would do it too, but we should get this one 20/17 from that fraction. In fact, you know what, I'm going to extend that here like this, okay? Now we got base x's as well. I got x to the power of 10. Do a better zero than that. There we go. 10, there we go. all over x to the power of 7. So see how I'm separating the bases almost like we would with like terms when we're solving equations, right? Well, this would be the same as x to the power of 10 minus 7. Remember, it's always the numerator exponent minus the denominator exponent. That's going to be x to the power of 3. Now, where does this x to the power of 3 go? Does it go in the numerator or denominator? It's in the numerator because, see how there was more x's in the numerator than the denominator? That means it has to remain in the numerator. So that's x to the power of 3 in this numerator. I'll show you a different way to write it, but hopefully we understand that it doesn't make a difference. Now I can work with my base y. So you had y to the power of 20 all over y to the power of 6. Well, it's the same base being divided. So I'm going to take the same base, the numerator from the numerator exponent, subtract the denominator exponent, and 20 minus 6 is going to be 14. So I end up with y to the power of 14. Again, there was more y's in the numerator here than the denominator. So there should, in the end, be more, there should, in the end, be y's in the numerator. Y to the power of 14. And that would be considered fully simplified. Like I said, there's a different way to write this, and I think Canvas will take that answer right there, but you could have just written the fraction 20/17 like this, and then your x to the power of 3 and y to the power of 14 like this. These two mean exactly the same thing. They're just shown in different ways. Okay, so when you type in your fraction into Canvas, get out of the fraction mode, and then you can type these in if that's what you prefer to see. I think most students prefer to see it this way. I don't know. Maybe it's more pretty that way. But this is exactly the same thing. It's, mathematically speaking, we don't really care which one you do. Yeah, I divided the 40 and 34 by 2 because on the homework it will always want the most simplified form of fractions that are numeric like that, if you can. All right, unusual quotient of powers. That's where, we're dividing the same bases, just like we saw in that rule, right? But in the examples we saw, the numerator always had more exponent than the denominator. What do you do if they're equal? Well, let's find out. Like this one, okay? Now, if we just apply the rule to this, what we end up with, it is the same base of 7s right there, right? But I'm going to take the 6 from the numerator, and I'm going to subtract the 6 from the denominator because it is division of the two bases right there. Sorry, I made that kind of sloppy. Well, what the heck is this? Well, it's 7. 6 minus 6 is going to give you an exponent of 0 on this. Okay, what the heck? Exponent of 0? Yeah. Look back here in the beginning. This is 7 to the power of 6 divided by 7 to the power of 6. Now, I just barely said this. But if you ever just take something, doesn't matter what it is, and divide it by itself, you end up with 1. Anything divided by itself is 1. Now, you know what? I'll expand it just because I think I can do it without too much trouble anyways. There's 2 7s. There's 4 7s. And 6 7s. There we go. Right? And what were we dividing this by? Well, 6 7s. Just like this. So you see what happens right here? Every one of these 7s, one in the numerator, one in the denominator, is going to match. And anything divided by itself is 1. Now it just expanded, right? So you can cross that out 6 times right there like we did, or you can cross it out once right there like we did, like you could do. And you'd end up with 1. Boom. For numeric type problems like this one, it will not want you to put this answer right here. It's going to want the value of 1. I'm trying to think. Now, even if the base was a variable, I think that the answer it would want would be 1 because that would be the most simplified format of the final answer on that. One thing we'll understand from this is that anything to the power of 0 will always be 1. Anything. Okay, so something like this. Once again, I'll take the shortcut. I definitely do not want to do 201 of these t's on this, but it's the same base t. Take your numerator exponent and subtract your denominator exponent. Well, anything subtracted itself is 0, but anything to the power of 0 is just 1. And again, we got to look past all these rules and stuff and just remember some of our old basic rules. Anything divided by itself is t to the power of 201 all over t to the power of 201. It is itself. You could have just made that you don't want to make it a phantom 1, but it's 1. Anything divided by itself is 1. I really like these types of problems because anything divided by itself is 1. Hey, I can do these all day long, man. So, once again, anything to the power of 0 means that you've pretty much taken the base and divided by itself, which is 1. It doesn't matter what this base is. Okay, it could have, it could be in parentheses, it could be, well, kind of negative. It could be whatever. It's just anything to the power of 0 is 1. Yeah, there we go. So now this exponent right here. Let's make this bigger. This exponent of 0 is being applied to everything on the inside. Now you could say, well, I'm going to distribute this 0 and make it 4 to the power of 0 times x to the power of 0. Well, that'd give you 1 times 1, which is, as it turns out, 1. Now, did you have to do all that work? Of course not. If you see anything to the power of 0, just say that it's 1 and be done with it, okay? There's no need to really do all this extra work. You're welcome to, just it's not necessary that you do that. So that's what we see there. Powers of 0, if you see an exponent that's 0 for a base, that is going to be a 1, automatic, okay? Well, what if the denominator has a bigger power than the exponent? Well, we know it's subtraction, right? So that just indicates that you're going to end up with a negative exponent, or it actually means that in the end, because we don't necessarily, as far as I remember, we don't want any answers on Canvas that have negative exponents. So you're going to have to change this into its fractional format. Okay, so remember, it's a higher denominator power on this. So it'd be like, I don't know, x to the power of 4 all over x to the power of, I don't know, 7, okay? Well, see how there's more x's in the denominator right here? That means that in the end there's going to be more. There needs to be the x's in the end in the denominator right here. In this case, it'd be 3. Now, sometimes students get a little confused with this because, well, what the crap is in the numerator? It's a phantom one. I'll demonstrate that here in a second. But this is the rule. Negative exponents tell you that you're going to take the base and the positive exponent, just put it in the denominator. Another way to do it, another way to say this is negative exponents reciprocate the base. But that means they also change the sign of the exponent, okay? Now, the reason why I'm putting this sentence here for the reciprocation part is because it is possible to have negative exponents in the denominator, which if there's nothing else to combine it with, you're going to have to reciprocate that in order to force the denominator to change its sign, or the exponent to change its sign, which will then make the exponent a positive. We'll see if there's an example here. Here we go. Just write this with positive exponents. This negative exponent garbage, and we don't really want it there. So let's make it an exponent. Now, this means that you'd have, instead of x to the power of negative 5, it's x to the power of positive 5, and then you have this 1 in the numerator. So it's 1 over x to the power of 5. Hey, well, that's written with the positive exponent. That's good enough. Now, if you think about this with the reciprocation, though, it's really x to the power of negative 5 over 1. What did we do? We reciprocated that and then changed the sign from negative to positive right there. Okay, so it's the same thing. However you want to think about it is good. If you want to think about it in this reciprocation format, that's fine. But if you just want to say that your negative exponent makes a fraction, that's fine too. All right, what about 6 to the power of negative 1? Yeah, remember, on Canvas, pretty much all the answers will need positive exponents. So I'm going to make that 6 to the power of 1 now, but in the denominator. And remember, that would have been 6 to the power of negative 1 over 1. Just reciprocate it. Make it 1 over 6 to the power of 1. Power of 1, I don't really need to see that garbage either. So I'm just going to make it 1 over 6. That's good. All right, what about 8 times y to the power of negative 7? Now, here's a common mistake we see with a problem like this, because, again, we get kind of robotic with this stuff. Students will say 8y to the power of 7 like this, put a 1 over it. That's pretty fancy. It's incorrect, okay? Because if we go back to the beginning here, the 8 has a power of positive 1, not negative. It's not negative, okay? So I'm not actually reciprocating the 8. It will stay in what will be considered the numerator. Because you can put anything over 1 like this, right? So when I change this into a fraction, that 8 with the power of 1, it's going to stay in the numerator. It's just the y to the power of negative 7 that's going to flip. So where it was a negative exponent, if I put that in the denominator, it will become a positive exponent. I've heard this before. It's a little bit of a gimmick, but with exponents, if it crosses the fraction line, then change the sign. See how it rhymes? Whatever. If that helps you, then feel free to do it. Whatever. I mean, that one it proves to be a little bit more tricky than we wish it was. It's not really meant to be tricky. It's just to help you understand that this 8 has an exponent of 1. All right, here we go. Yeah, this is one where the negative exponent is in the denominator. Remember, that would indicate that we're going to reciprocate that fraction. So remember, cross the line, change the sign, boom, there you go. Now you could make it x to the power of 8 over 1, right? We reciprocated these two values. But to make that fully simplified, anything divided by 1, just make it a phantom divided by 1. It's there, we just don't want to look at it in order to consider that fully simplified. And yeah, this one proves to be a little tricky because students get so used to just kind of forcing these into the denominator. Well, if it's already there in the denominator, it's kind of like it was forced into the numerator instead. So it just switches. Here we go. Yeah, like this one. Okay, so these two bases are different. You got an x base and a y base. Okay, so it's still a fraction, but again, this x to the power of -7 right here, all I got to do is move it to the denominator, and that will change the sign of the exponent. Same with y to the power of -4 right here. Well, all I got to do is move that to the numerator, and it now has a positive exponent. That is all. That's pretty good. There's all our rules, and we're showing a little bit extra rules. This one was just kind of our power of power rules right here, just applied to fractions. Same with the power of product kind of thing. Remember, you're just applying that exponent to all the values on the inside of parentheses. Same with this one. Negative exponents are going to kind of flip that fraction. It's just a reciprocation. Anything to the power of 0 is 1. The quotient rules, when you're dividing the same bases, just take the exponents and subtract them. The product rule tells you to take, if the bases are the same, being multiplied, then you add the exponents instead.